Well, thank you for joining me after lunch. I know it's not the easiest thing to do. I myself had my thoughts about coming here and speaking right now, but I'll be speaking about Git and how we use it as Shazam, give a bit of an overview for those that don't know what it is, and then get into some details. Let's get this stuff out of the way. My name is Savvas, as already been introduced. I'm a senior software engineer at Shazam. You can find me on Twitter at geeky_android. Where I will be posting a link to these slides afterwards. So, what are we talking about? Obviously, we're going to talk about version control, specifically Git. Who here uses Git? Great, I can skip the introduction slides a bit quicker. Who here thinks of themselves as not an expert per se, but a skilled user of Git? Hopefully this talk will be for those that didn't raise their hands. There's other version control systems, obviously. There's Subversion, Mercurial, Perforce. Lots of companies use different things. We're going to be focusing on Git now. Why do we use version control? This is a picture of an old hard drive, which was on that PC that I was mentioned that I got when I was 7, where I recently recovered from a storage unit somewhere in Greece. And I found old projects that I had that I wrote when I was a kid. And it was really exciting going through all the old stuff that I wrote, but many of these things didn't compile anymore. The code, of course, was horrendous. I was a kid. And everything was unorganized. It was basically a big folder filled with subfolders, and I didn't know which folders related to other projects. It was a mess. So I had no history of what I was doing when I was doing these things, because I couldn't also try to fix the code. I had no idea what the code was supposed to do in many cases. And yeah, there was no organization. So source control can help you with that. Also, when you're working in a team, regardless of the size, I would say that version control is imperative. You see there's many people that try to commit. You can step on each other's toes, and that can be a real pain to try and fix all these conflicts. There's also accountability. Not necessarily in a bad way, but when you come across a piece of code that's a bug in it and you might not quite understand what it does, you can also always look back in the history and go to the original author if they're still part of your team and ask them to help you. Otherwise, that's not that easy. Also, when your team grows, this is a map of all the offices that we have around the world. We have about 7 offices, I think now, yeah. When you have people working remotely across many different time zones, getting everyone committing to the same repository is very tricky, and Git is really good at that. Yeah, it helps with your day-to-day workflow. I keep hearing that my voice is cutting off. Is that just me, or? No, it's okay. Yeah, so it also helps with continuous integration and continuous deployment. There's a lot of companies that work primarily remotely, and Stack Overflow is a good example of that. Git itself is developed by an international team, Linux itself, and GitHub is one of those companies. And using Git is really helpful. Now, how? Before we get into the details of what I want to talk about, we need to understand a tool that we use in order to gain the most out of it. And a lot of people use Git in a very sort of linear flow, in a very simple workflow. And that's very good for most cases, but when you know all the things under the hood, it will allow you to make better decisions on how to organize your day-to-day workflow. So to begin talking about Git, I will compare it with a known quantity. Known it was in the old days. This is another question for you. Who here knows what SVN is and how it works? Okay, fewer people than Git. So maybe this comparison is not that great, but you can sort of also use this as a comparison between two different types of workflows. So these are the main differences between Git and SVN, but like I said, it's about the workflow specifically. Git is a distributed system, while SVN and other repository systems are centralized. What that means is that in a system like SVN, you have a central repository sitting somewhere on a server. And you have your users that check out that repository, and when they need to commit code, they push that code to the remote repository. Their copies of that repository is just a mirror of that remote one. Git is slightly different. Every time you check out, you clone a repository, you are actually creating a copy of that repository. Your copy is an actual full-fledged repository itself. And there's no need to have a centralized source of truth, even though that's how most people use it. So you can have 4 users all checked out that repository, and they all Usually you push in one centralized one because you want to promote your code changes to your other team members, but there's no need for that. You can actually have repository 2 talk to repository 4. You can go crazy and have all repositories talk to each other, which of course you would be crazy to do, but it allows you to do that. Git can work offline while SVN and other repositories can't. In the SVN example, if you have network connectivity, every time you want to promote code, which is called a commit, you push your code to the central repository. That action of pushing your code across the internet or your local network is called commit. On the Git world, it's slightly different. Well, of course, yeah, if you don't have connectivity, your commit cannot go to the remote repository and you're stuck. If there's no connectivity for any reason, your local network went down. There is some problem with the internal network, I don't know, cards. So until that problem is resolved, you are basically stuck, you and everyone in your team, and you can't continue working. Whereas in the Git model, if you have no connectivity, your commits are local. Committing is a local action. You can have many commits queued up, and when you have connectivity, you can promote those commits to the remote repository that you're working against. In Git, the unit of operation in Git's world is a commit, whereas in SVN is a revision. Those are slightly different concepts. A revision is sort of a snapshot of your entire repository at a moment in time. Even though that's not technically how it's stored on disk, the unit in which SVN and other systems work is a revision. So every time you make a change, you're basically creating another snapshot of your repository. Even though it doesn't take up double the space on disk, the logical unit is a whole snapshot. On Git, a commit is a self-contained unit. It only contains changes that you've made and information about where that change was made in relation to other commits. I will get into detail in a bit. This effectively creates a linked tree of commits. And this model is very useful to have in your mind to conceptualize how Git works. In Git, the content is saved as metadata. In SVN, the files and the metadata are separate. This is a very minor distinction. You may have seen those .something folders in your directory, like there's a .git and a .svn. Those are hidden folders. In Git's world, everything, your entire repository and the history is saved in that .git folder. And everything outside of that is your working directory. It's basically a snapshot of that whole repository at a moment in time, let's say. Whereas on SVN, it's different. The .svn folder just contains the metadata, and the actual repository is stored in and all the branches and stuff is stored outside of that. The branches in Git are just commits. I will explain in a bit what I mean by that. But in SVN, the branches are folders. So getting back to the SVN diagram here, you may notice that the top level folder is a project, and there's a subfolder called branches, a subfolder called trunk, and a subfolder called tags. So every time you create a branch, you're effectively creating a new copy in your local file system. Not with all the files in it, but all the files that are basically different from that branch from, let's say, trunk. So it creates a mess. Trying to integrate branches is a nightmare in SVN. It's just not fun. In Git, a commit is a cryptographically secure, identified by cryptographically difficult word, secured hash code. A commit contains a diff. This is basically literally a diff between the previous commit, just the contents that have changed, basically. Some metadata. The metadata can include the author of the commit, the date that the commit was made on, stuff like that. And also a link to the previous commit's hash. This is very important. All these three pieces of information, there's some other stuff as well, but these are the important ones. These three pieces of information are encoded into a hash which identifies this commit. Now, if any of these things changes, the commit is considered to be a different commit. Even though the contents might be the same, if you change the author name, you've now created a new commit, even though it looks the same. That then gets put on top of the accompanying tree. Let's see that there. And that link that we said that points to the previous commit would point into that brown dot right there. So a branch on Git is literally just a name for a hash. So when I say feature 1, and that's my branch name, that it literally translates feature 1 becomes A4BGF3. That is the hash code of that commit. There's nothing special about it. So a branch is simply a label. Now in Git, you can change history, and in SVN you can't, and in some other revision-based systems. So let's say you have 4 revisions here, and you want to change, you want to remove the third one. You committed something that you shouldn't have. We heard in a talk previously that you should never be pushing your passwords and your key stores onto the repository. If you do that, you can't change history in SVN. It's always there. If you want to change history, you simply have to create a new commit that sort of reverts the thing you wanted to remove. But that commit is still in history. You cannot remove it until you have access to the physical storage of where the SVN repository is saved, and you don't want to mess around with that. We used to do that in the past, and it's a nightmare. In Git, you can still create a new commit, of course, to revert an old one, but Git will allow you to take a commit and literally remove it from history. It's like it never happened. And when you do that, the top commit there, that's the green one, that's 4A, CA, whatever, is going to be attached on the previous commit. After you fix any conflicts, if they are, you will then assign a new hash, because like we said, when one of these pieces of information changes, the commit hash changes. So even if the contents were the same, you will now assign a different hash to this commit, and everything is happy. This is not recommended. You should avoid doing that for when you're pushing changes, because when you do this, you're changing history, and if your team members have a copy of that repository, now you have a conflict in the tree structure. And that can be resolved, but it's just a bit fiddly and manual. So this is very useful for local commits. So if you have 5 local commits, before you push them, you can go and remove any of them you want. It doesn't really matter. You're not affecting anyone. And also it's helpful for when you want to remove sensitive data from your repository. We actually had to do this recently. We used to push the key store as well in our repository, and then we went back and changed history. So now no one has access to it. Now before we continue with how we use Git, let's talk about how remotes work. Now in Git, like I said, every repository is a full-fledged repository, but there needs to be some way for you to talk to a remote one and push your code. So that's the idea of where a remote comes in. Now your local repository is a direct clone of the remote repository. You'll notice that all commits have the same hash codes on them. Now the name of the repository is not really important. It doesn't matter how you call them. We usually call the remote repository origin, but you could call it Bob. It doesn't really matter. You can have multiple remote repositories and push to either of them. This is how you usually work with GitHub when you want to work on a fork. So if you forked another project, you have 2 remotes, one for your GitHub project and one for the upstream, as we call it, project. But again, you could call it Bob. Now your master is not the same as the remote's master. What do I mean by that? In the remote repository, there is a label called master, pointing to a hash. You have the same label, pointing to the same hash, but your master label is not the same as the remote's master label. For that, you have another label called origin, or Bob/master. Every time you change your master, the origin one stays where it was. And every time you want to push code to the remote one, you basically have to make sure that the remote master is still pointing to origin master, so no remote changes have happened. And if that's the case, you can push your changes on top of that, and then the remote master will point to the same hash as your local master. So what happens when there is a change in the remote branch before you're ready to push your changes? So let's say you have a local commit. Now your master points to a completely different hash, and the origin master points to the same thing as the remote repository for now. If there's a new commit that some team member pushed, master and origin master, well, the remote master and your origin master have diverged now. So you have to resolve that somehow. Now the typical way that people tend to resolve this is by doing a merge. So what you usually do is you do a pull or a fetch, and then you have a local version of the remote hash. You can see that green dot on the right side there. And then your local commit sits on the side of it, and you have to resolve that difference between these two by creating a third commit that merges the two changes. And now your master is this new commit, okay, AAC, the purple one. And you are now, that commit lives on top of the remote master commit, so you are allowed to push. But you may have noticed that there was my change, there was the remote change, and now I have a third commit for no reason other than just resolving this difference. So that third commit doesn't actually add any information. I personally, don't like this. I'm a bit of an OCD when it comes to my branch structure. I want to resolve this somehow differently. Git allows you to do that by using what is called a rebase. So getting back to the situation where we had before, you can resolve this by actually setting aside your local commit momentarily, fetching the remote commit, so now your local repository is the same as the remote repository, and reapplying your commit on top of the remote one. Now, by doing that, like we said, if anything changes in those 3 bits of information, your hash changes, so this will now be a different commit. And you are now allowed to push this remotely. You may note that the old commit is still sort of staying there on the side, not referenced by anything. Git doesn't forget, unless you instruct it to clean itself up. Anything that has ever been committed to your local repository will be still there, and it will have its own hash, but when you usually look at your Git tree, you will not see those things because they are not referenced by any label or by any other commit that eventually is referenced by a label. So these are hidden commits. You can clean them up. I will show you later how to clean them up and how to reference them. So now let's get back to how we use it. Our branching strategy is very simple. We always push on master. We branch when we're ready to freeze a release. Now, every time I say this to people, they think I'm crazy. It's not a very common pattern in the mobile world for some reason. Backend teams and server teams have been using this for many, many years. It requires a lot of prerequisites, though, for it to work. So it's not an easy thing to do, but it's very much worth it, and I will explain why. This is how our tree would look. I put it horizontally because vertically there was not enough space. So you can see that basically that top line is our master branch. Everything is committed sequentially on top of everything else. We may have local commits that, or local feature branches that live maybe for a day, but they get always rebased on top of master, like we showed before. So if I have 3 commits and I come in the morning and someone is pushed, I will rebase my branch with my commits on top of master. And when I'm ready to push, it will go to master. It will not go to its own feature branch. When we're ready to cut a release, you can see those 2 big pieces of parallel branches there going on. We basically create a branch. We tag it with the name of the release and an actual Git tag. And we cut a release candidate from that. It goes through some last-minute manual verification stages. And when we find bugs with those, we fix them on that branch, and we keep merging them back to master. This allows us to have people working on the next release and people just sort of bug fixing and stabilizing the existing one until we actually push it. Now, to do this, you have to basically have some prerequisites. Those prerequisites are you have to do BDD and TDD almost religiously, because if you allow anyone to push to master, you're basically inviting people to break your code. So unless every single piece of functionality you're writing is covered by a acceptance test or a lot of unit tests, you shouldn't be doing this. We now have the confidence that every time we push, if everything goes green, then we're good. Master is okay. For that to work, you need to have CI. So the process that we follow at Shazam is every time you push code, before the code actually ends up in the remote repository, we have a Git pre-commit hook that basically, let's say that I have 3 commits on top of master. The pre-commit hook creates a local, a new branch name, a new label pointing to my master, pushes that remotely, and a build box picks that up and builds it. Runs the entire test suite. We have about 500 acceptances at this point, and God knows how many thousands of unit tests. When everything goes green, my change is allowed to be pushed to master. If I've broken something, I can't push. While this is happening, if any other team member tries to do the same, their commit will fail immediately because they will be informed that someone's running an integration, as we call it. Now, of course, to do this, you also have to make sure that your entire build doesn't take ages. When we first started doing this, we only had a flow where we had like 2 or 3 devices, but we would run all our acceptances to all those devices. I'm not going to get into details on that. There's another talk that we've given. You can find this online about how we do testing at Shazam. But the basic idea is that we shard all our tests across many devices. We have about 10 or 15 devices, and every time we run our entire test suites, the whole thing takes about 4 to 5 minutes. So that's not really a big problem for us, at least. We're a small team. We can manage that. And this allows us to have continuous integration, real continuous integration. This also, to allow you to do this, you also have to have your code structured in a very modular way. You have to be able to turn things off if a feature is not ready. You have to be able to turn it off immediately and be able to cut a release. Because if you are in the middle of a huge refactoring that has broken everything, you can't cut a release. You have to roll back changes, and we don't want to do that. So server teams usually do that by having what is called a feature flag, where every feature is hidden basically behind a global flag, literally just a Boolean flag that enables or disables a piece of code. We do this by dependency injection. We try to write our code in such a modular way that when we need a new feature, we have a new dependency that implements that feature, and by default, you have the old implementation, and you just swap these things out. So you can turn things off and on. It's not very easy, but it's doable. Yes, rebasing is very important here. You have to rebase all the time. Every time someone pushes, I rebase my changes, because what this allows you to do is, the main problem with merging conflicts is when you have a very long-lived feature, or two of them running in parallel, the first one that integrates to master is lucky. The second one is very unlucky, because now you have to have basically 7 or 8 days worth of code compared against other 7 or 8 days worth of code. And you have to fix all those conflicts in one go. And that's very, very difficult if you're working on the same things. When you're rebasing, what Git does is it will try to apply all those commits sequentially, one by one. And if there's a conflict in the first commit, you have to resolve just the conflict with one commit. If you keep your code very short, as you should commit very small pieces of functionality. Fixing those conflicts is a piece of cake. And also, yeah, if you keep doing this all the time and you push your code regularly, you never have integration problems. Yes, so this is how we do things. Why we do this, I've touched briefly on it, but one of the key benefits we get is that this keeps us true. Enforcing slightly, we don't actually have like any rule that is that, for instance, you can't push. You can still push a branch, but we enforce it within ourselves in the team. By doing this, it forces us to do all these good things that I've talked about. It forces us to think about, oh, have I broken anything? I don't have an acceptance test for this thing that I'm building. I should write one. It makes us think about all those things that you have to do before you do this every time you push. BDD, TDD, and having your features modular. It produces a clean and easy tree to understand. As you saw, there was nothing to our branching strategy. It's just one line, and occasionally you have a second one running on the side. This is also very useful for when you have new team members joining the team. There is there's no learning to do, basically, about how you structure your code. It's literally master, and that's it. We have no code integration problems. I can't remember the last time I've had to resolve a conflict that took me more than 10 minutes, maximum. And that was, 10 minutes is not very usual. We usually spend like a minute or two on them. It allows us to do quick releases. Because our master is always production ready-ish, we can cut a release on a moment's notice, and with a very, very quick, maybe like a day, maximum 2 days of like sort of strengthening work, we have releases that are ready to go to all our users. We have millions of users. Turning off issues is very easy, because the number one step forced us to keep our code modular. So when we're, let's say I'm building a new functionality and suddenly we realize that for whatever reasons a product owner wants to release tomorrow, I can just switch off that feature that I haven't written and we're ready to go. There's not a lot of work that needs to be done for that. And it allows continuous deployment. We don't do continuous deployment because it's crazy to do continuous deployment on mobile clients. If you push more than once every few weeks, users get really annoyed for some reason. But our server teams use this sort of flow as well, and the only reason they don't push to production every time they push their code is because the SEs need to run some final checks. So we actually have had to put a manual step before code goes to production by pushing a button. But we can have continuous deployment anytime we want it. We don't do this on mobile for those reasons, but we could get very, very close to having a continuous deployment system. Now, this might not be for everyone. I get that. It's a very tricky thing. I was one of those people that were really scared when I heard about this flow. We used to do branches. It depends on the size of your team and the way that you work. There's also some other considerations. For instance, if you're working in an industry where you are basically being, you have to follow some rules, like say you're in a bank. Every code has to be reviewed by at least 2 people. You can still do things that are very close to this flow, but depending on your needs, you might not be able to. It might not be the right answer for you. It might just not work for the way that you and your team like to work. But what I would say is that you should give it a try on a small project, maybe to begin with, and see if that actually works for you or not. Just don't dismiss it just by virtue of hearing it. If that's not for you, what most people do is either a variation of or something called a Git flow. Git flow became very popular a few years ago. There's a link to the blog post that proposed this model. The slides will be up online, so you can copy it from there later on. Git flow is basically a not very complicated model. It looks a bit scarier than it actually is. I don't have a pointer, or do I? I'm not really sure. But basically, the idea is that you have a master branch on which you never commit, and you have development branches for each version. So the idea is you have a version that's running now, so that branch has been branched off, well, in this case, let's say a previous master version. So you develop on that branch. It's called the develop branch. You either commit on that branch directly. If you have, let's say, a very small fix, I need to change that, padding on that button there. You just push onto the develop branch. But if you have a relatively long-running feature, you branch off of that develop branch, and you develop on it. And your other team members have branched off the same branch at some other point, and they do their own thing. You keep merging your develop branch into those feature branches as often as you can, so that you're always up to date. And when you're ready to commit, you merge that develop branch that feature branch into the develop branch. That's the point where you have to do conflict resolution if someone else has pushed in the same time as you and you haven't actually fixed those conflicts. And this is where, you may have to fix a huge conflict of, let's say, 7 days worth of work. But once you do that, your feature is integrated. And when you're ready to release, you branch that develop branch into a new branch called the release branch for that specific version. That is a release candidate, and when you're ready to, it goes through some testing. If you find some problems with this release, you may do hot fixes on that release branch directly, or create new branches of that release branch, which are called hot fixes branches, and then merge them back into that release branch. And when the release is ready to go out and it's stable, you merge that release back into master and tag it at that point. And then the next version basically gets branched off from that point. It sounds a bit more complicated, but once you actually get your hand around it, it's not really difficult. It's not more different than most people do anyway. This just sort of imposes some structure, so that if you're working in a really distributed and large team, this imposes some restrictions on, so you can't really go crazy and ruin it for everyone else. It's very popular. You can also give this a try if you're not really using it. You can read it from that blog post. There's a very good explanation on how it works. Now, before I go, and I'm sort of running out of time, not too much, I'd like to give you a few tips about some helpful commands that I use at Git almost every day, and they have really helped me to increase my productivity. So assume you have a repository. This is a very simple repository that has, like, say, 4 commits. No branches, nothing fancy. The most useful commit in Git, I think, is rebase. Now, we've already talked about rebase, but an interactive rebase with basically rebase-i allows you to do things that might be considered crazy. So the syntax is rebase-i, and then you either give it a hash or a relative path. So in this case, I'm saying head, take 3 steps back from head. Head is the current checked out branch, or the commit that I have. 3 commits before that. So what this does is it picks those 3 commits, or the range from your current commit to the hash that you've specified, and gives them to you in a list, a reversed chronological list. Now, actually, no, sorry. The just normal chronological list. What this allows you to do is go to each commit and change what you want to do with it. There's a big list of commands there. I don't know, from the people in the back there, you probably won't be able to see this, so I will read them out. Pick is the default option. That literally goes, just use this commit as it is. You can actually delete a commit. This is how you delete a commit from a history, like I talked about before, by literally removing that line. If I go to that second line and remove it, the commit that is in there, which is called the third commit, will basically disappear from history. Because Git will go, get the first line, it will pick that, then it will go to the second line, pick that, the other commit disappears, doesn't exist. Even though it still exists in my repository, it doesn't exist in this new branch that I've created. You can reorder commits. I can literally go and change the order of those lines, and Git will apply them in that new order, fixing conflicts as you go along, of course, because not always, like if you flip commits around, you might not always get a working piece of code. You can reward, you can edit a commit. By using the reward command, you can basically use that commit, but edit the commit message. So if you've made a mistake, before you push, you can go and edit the commit message. You can edit the, yes, thank you. You can edit the contents of the commit as well. If you use edit, Git will stop when it applies that commit, and you can go and change the code before you continue. So if you made a mistake, you can actually go and change history in that way. You can merge two commits together by squashing them. If you basically change that name to squash, it will basically pick that commit and the next one and try to create a new one based off the diff of those two commits, and you can then choose the name for that merge. Yes, those were the commands. So forcing labels. Now Git, like we said, a branch is nothing but a name for a hash. So I can literally take the name and just move it somewhere else. So in this case, we have a very simple structure there. We have origin master and master pointing there. I can take master and move it a commit down. I can do that by literally saying reset --hard to a hash. This will take my current branch, in this case it will be master, and literally move that label down. You can do that when you want to, let's say for instance, you want to get rid of that remote, that origin master commit. I can move my master one step back and force push that change remotely. And that commit now disappears from the remote branch as well, the remote repository. Finding lost commits. Like I said, Git doesn't forget anything. So even if you delete commits or if you just move them out of any reference point, you can always get them back by doing a ref log, a reference log. This will basically print out a list of all the places that head has been in the past, you know, however long that list is. So you can always find a commit that you were on if it has disappeared from your list. Updating other branches. This is useful when you are on a branch, let's say in this case we're on master, and I want to merge from that other branch into master. We do that for our release branches, but my label for that branch is not up to date because someone has pushed on that branch from another team. So I could go to that branch first of all, I could check that branch out, fetch it, get it up to date, then switch back to master and do the merge. But I find that very boring and repetitive, so you can actually use this syntax. You say fetch origin, the name of the branch, colon the name of the branch, and this will literally just update the reference of your local label to the remote label. Nothing fancy there. Taking commit from another branch, this is also very useful. Cherry picking. Sometimes you're on, let's say, a release branch and someone has committed something on master that you really want on that release. You can't rebase, these are completely different branches now, so you can literally go and copy that commit over to your branch. This will basically copy that commit, bring it on top of your current point, and as I said, if anything changes, in this case the link to the previous commit has changed, the commit will have a new hash, but the contents will be the same. Git also remembers cherry pick, so when you merge them back, it will know that, oh, this is the same thing as that one, and there were no conflicts, so I don't even need to think about resolving them. Deleting a remote branch. If you have long, short featured branches, like I do that usually when I have 3 commits that I'm not ready to push yet because there's, let's say, some problem, like a unit test is not passing, but it's the end of the day, I will push that branch remotely so that the next day I can come in and work on it. But in the meantime, if I get hit by a bus, someone can pick up my work. So when I do this and I merge it back to master, that remote branch is no longer needed, it's dead. So you can do that by pushing to the remote, in this case origin, by saying colon and the name of the branch, and this will just delete that branch from the remote. But of course, other team members may have already fetched that and actually have that locally. So this is sort of the reverse of that. If you prune your repository, it will basically get it up to the same state as the remote one. It will basically go, oh, I have these 3 branches and the remote one doesn't. I need to get rid of them. And this is what this does. Updating all commits without changing history. Sometimes you want to go back in time and add information to a commit, but you don't want to change history because if you go a year back and you change one commit, everyone has to change their entire repository, which is a bad idea. But sometimes let's say you forgot to mention something on a ticket, on a commit. You can literally attach notes to commits with a git notes command. These are metadata that do not take part in the calculation of the hash code. So you can modify this as much as you want, you can add them, you can remove them, and the commit is still considered to be the same. But now your, let's say, ticketing system can pick up the commits for, let's say, a ticket number, because you forgot to add it, you can go back and add it as a note. Searching. I'm not going to get into details here, there's also a link on how to use this. This allows you to search back in history, either on commit messages, so you can say, when did I reference this ticket? And it will give you a list of all the tickets that have that in their commit message. Or you can search contents within the commit. And you can say, when was the first time that, when were all the times in the history that the word person repository has been modified? And this will show you additions of that repository, moves of that word, anything that changed that piece of word that you put, that regex that you passed there. This will basically create a list of all of them. This is the second most useful command on Git, and this is my last slide. Bisect. When did we break this? Many times, I actually had to do this the other day. You find a bug that you know you didn't have last time you released, and you can verify this. So you now have a commit that has a bug, and a commit, the previous release, that doesn't have that bug. So you know these two things. You have your master, or the hash, and the hash, or the label of your previous release. You do a bisect, and you say, that commit is bad, that commit is good. Git will then start doing a bisect, that's why it's called, by going to the middle commit of this entire tree, and it will allow you to check whether the bug exists or not. You check if it exists, you say it's good or bad, and then depending on what you said, it will basically go to the second half or the first half and bisect that. And keep doing that until you find the commit that introduced this bug. Let's say if you have like, hundreds of commits, you can do this within a matter of minutes and figure out exactly what commit broke it. This is very, very useful. Use this. And that's it. There's going to be a link to the slides. You can find that. I will post that on Twitter as well. We're also, of course, hiring. Any questions? Yes? You have like less than 5 minutes for the questions, so.
Just one question about the commit hooks you use to verify. Does that mean, when do they execute? When you say git push, the push actually hangs and waits for the commit to complete and rejects, or is this local or server-side?
So this is a local commit. This is a commit hook that runs a Gradle task. A Gradle task that I wrote that literally looks at the current branch that you're on, and it will run this logic basically if you're on a master branch or on a branch that starts with the words ongoing, which is the name that we use for our release candidate branches. If you're in any other branch, it will just push it normally. But for those branches, it will literally say, okay, I will create a new branch of the current commit, push that remotely. We have a Jenkins plan that automatically picks up commits with that branch name. It will run it, and your command line will literally start updating the output of the Jenkins job as well, so you can see it building. And when the build finishes, if it's successful, it will continue with the push. Otherwise, it will fail and tell you, I failed. So, yeah. Anyone else?
Hello. You mentioned that basically push everything to master. You don't have other branches other than the release branches. So how do you avoid problems without having a code review?
Code review. That would be one of the things that, depending on how your team works, might be a reason why you wouldn't use this. We, in our team, don't do code reviews, but we do a lot of pairing. So we guarantee quality that way. But if you are enforced or you want to do code reviews in your team, there is a way to do something very similar to this by having very short-lived feature branches that literally just branch off master for, let's say, 2 or 3 commits and then merge back immediately, as long as you don't have these running for like 7 days. So you still have sort of master only, but it's not really master only, but you can do code reviews.
Just a quick question. You said you do pairing. How do you do that with seven offices around the world?
So this is tricky, because we used to we're not in that situation now, my team specifically. We are co-located, the Android team. We used to have a member who was in the States. So for his commits, we used to do a run like we would come in every day and we would see the commits that he made. So there was some sort of discrepancy there. Like, yeah, we could have done the code review branching thing at that point, but we didn't. We now no longer have this problem, but depending on how you work, yeah, if you have a really distributed team, this might be a bit of a problem. But you can always sort of take the essence of this is not necessarily having only one branch, but the idea is that you're always developing on something that is production ready. As long as you can do that in any way, I would say that's a win. Keeping it clean is also very, like, I like opening my Git tree in the morning and seeing just one line. That's what I want to see. Anyone else? I guess not. Well, thank you very much, and yeah, cheers.